This image shows the evolutionary tracks for contracting protostars. So when you start out, they all have roughly the same temperature. They're all big molecular clouds. And the bigger ones, the, say 100 solar mass protostars, are going to be brighter just because they're bigger and they have more surface area. Um, so they all start out about the same temperature, but at different luminosities on the HR diagram. So as they contract, at first, they just get less luminous. And that's because at first, as they contract, heat is able to escape. But once they get down to a certain point, and you can see that as the kind of elbow in these tracks, then they get dense enough that they can actually start to accumulate heat. And that's when they start to actually get hotter and then to the left on the diagram. And then eventually they get hot enough in their cores to ignite hydrogen fusion, and then they become main sequence stars. And when that happens, they will end up somewhere along this line, which is the zero age main sequence. So larger stars are going to go through that process a lot faster. So a 100 solar mass star, which is a truly big star, will reach this nick point here at about 100 years, and at about 1,000 years here, and at about 10,000 years is all it takes to get onto the main sequence. So they very quickly start to fuse their hydrogen, and they fuse it very quickly. And then one solar mass star, such as our sun, takes a lot longer to get down to that point. So we're looking at 10 to the 7, so it's about 10 million years to get down to here, maybe 100 million years, and then eventually ends up on the main sequence, but much farther down. And then even smaller stars are going to take an even longer time to get onto the main sequence, to get hot enough to start hydrogen fusion. And so that is the process. That's how they track on the HR diagram.